This video is on solving basic quadratic equations by using what's called the square root property. These are the easier type equations usually to solve. And what I have listed here is the square root property. If you have something squared, in this case it's capital X, if something squared equals a constant, we're calling it k here, then x is equal to plus or minus the constant. So this is known as the square root property. And you can see that equations like this will have two roots typically. However, if the constant k is 0, then you would only get one root to the equation. And that's some of the equation terminology that we use. When you're solving for the variable, you're finding the roots to the equation. Sometimes we call them the zeros in reference to graphing. But just finding the value of x or finding the roots to the equation is what we're doing. So I have a few examples here. Let's start with something pretty straightforward. I'm going to remove the square root property. We'll bring it back if we need to remember it. But here's a basic quadratic equation. The exponent of 2 is the giveaway that this is quadratic in nature. So we're going to solve for the two values that we expect to get out of this equation. We're going to find the two roots to this equation. So this is one that we would look at as one that we can solve with the square root property. And there's a basic reason for that. It's the fact that the linear part of the equation is missing. In other words, there's no number times just plain x to the first power in the equation anywhere. It's just 4x squared minus 3 equals 25. So the linear part, we would say, is missing. So that's typically when using the square root property is going to be the way to go for solving that type of quadratic equation. So the first thing we're going to do is isolate the squared portion of the equation. So we're going to isolate x squared in this case. So I'm going to use inverses to do that. The additive inverse. So actually I'm going to go ahead and add 3 to both sides of the equation to cancel out the negative 3. So if we just add 3 right now to both sides, I'm going to put a sum line in since I'm using the inverse or the additive inverse. And then we just add things vertically. Now we are using sort of an abbreviated notation. Technically this would leave us with 4x squared plus 0 equals 28. But I'm going to go ahead and just use a canceling notation here. Kind of nice to use canceling on the fly. And this is going to be 4x squared plus 0, but we're just going to write it as 4x squared. And that equals 28 on the other side of the equation. The 25 plus 3 produces the 28 for us. Now, we can use the multiplicative inverse of 4 to isolate x squared. Technically, the multiplicative inverse of 4 is 1/4. So we can multiply both sides of the equation by 1/4. But again, on the fly, it's kind of nice to use division to make this happen. And technically, dividing both sides of the equation by 4 is equivalent to multiplication by 1/4 on both sides. So we're going to go ahead and just use division notation because it's kind of convenient here. So I'm going to divide out the 4 on both sides. And we can even show that the 4's divide out or cancel out, and that leaves us with x squared is equal to 7. So we're not quite done solving the equation. Now we have to extract roots or actually apply the square root property. And hopefully you can see that at this point we're ready to apply the property because we have the equation looking like this. We have something squared equals a number, or something squared equals a constant. So we have that here, x squared is equal to 7. So we're going to go ahead and apply the square root property. What this means then now that is x is equal to plus or minus the square root of 7. So a basic fact about square roots that hopefully you remember, whenever you take the square root of a prime number, you get an irrational result. That's actually a theorem from number theory. So 7's a prime, so we're taking the square root of a prime, so therefore the two roots to this equation are irrational. Now it's important to note that sometimes the square root of composite numbers are also irrational, but that has to do with the fact that those composite numbers break down as prime factors, and so the theorem still gives you some insight there. Okay, so anyway, I'm going to write the two roots separately and also as a solution set. So we can say x is equal to the negative of the square root of 7, or x is equal to the positive square root of 7. sometimes very practical to go ahead and do the approximations for the roots. So I'm going to actually use a calculator to approximate the square root of 7. So the square root of 7 is roughly, and I'm going to go ahead and round to the hundredths place, 2.65 actually, or 2 and 65 hundredths. Now, technically, my calculator display, I ended up with 2.64575 and a bunch of other digits. If I round it to the thousandths place, the 6 is in the tenths, the 4 is in the hundredths, and then the 5 is in the thousandths. Oh, actually, it looks like I rounded to the hundredths. So if we look to the hundredths place, that would be the 4. The 4 would look to the 5. Using traditional rounding, it would round up to a 5. So roughly 2.65 or 2 and 65 hundredths. Oh, no, it looks like I forgot my negative sign, so we'll put that in there. So that's the negative root, and then of course the other one is just going to be the positive version of that. So there's the two roots to our equation. Now if we wanted to, we can write that as a solution set. So we can say x is equal to, and then using set roster notation, we use braces, we could just put in the negative square root of 7. We usually list the roots in order. And there we have the set roster notation for the solution set. So there's the two roots to the equation, as expected typically with quadratic equations. All right, let's do another example. So this one has more terms in the equation, so there's a little bit of work that needs to be done before we can try to extract roots. Of course, that's going to be typical with most equations. So one issue is that we have the u squared on both sides of the equation. So we're going to have to fix that. And if you think about the technique that we're trying to use, we're using the square root property. That means we need to get the squared part of the equation isolated and then the number on the other side of the equation. So that's our thinking in terms of what we have to do to this equation at this point. So I'm going to go ahead and get the u squareds together. It's a good idea to keep your leading coefficient possible. It's kind of a regular habit when you're solving equations and inequalities. So that would mean moving the negative 5u squared. So the inverse of negative 5u squared is a positive 5u squared. So I'm going to go ahead and just add 5u squared to both sides of the equation. That's using the addition property of equality. And because I'm using the additive inverse, I'm going to go ahead and put a sum line in there. And so we add vertically, so we're going to get 8u squared minus the 12 equals just the 48. Because these two canceled out, those are additive inverses of each other. And I am kind of using lazy canceling notation here, but it makes sense to do that with equation solving, especially the more complicated your equations get. Sometimes we skip a few of the basic steps or try to abbreviate it a little bit. But anyway, here we are with a basic equation. This actually looks a lot like the equation we just solved. So now we're going to isolate the u squared. I'm going to use the inverse of a negative 12 and just add 12 to both sides of the equation. Again, I put a sum line in there because I am using the additive inverse. So those cancel out, the negative 12 and the positive 12. Leaves us with the 8u squared plus 0, which we just write as 8u squared. So technically speaking, when we have this 8u squared plus 0, and we just write it as 8u squared, we're actually applying the identity property for 0. Remember, 0 and 1 in algebra are identity elements. So we just applied the identity property of 0. So 48 plus 12 is going to give us 60. So I can kind of see in the long run that we're going to be dealing with fractions in this one. And we're going to go ahead and get rid of the 8 in front of the u squared by multiplying by 1/8. But again, on the fly, it's kind of easy to write it as division. But technically, division by 8 is the same thing as multiplication by 1/8. Okay, so those do divide out, or they cancel out, leaving me with u squared equals 60 over 8. And actually, we can go ahead and start reducing this fraction if you want. 60 divided by 8, it's going to give us a fraction, or if we want to go to decimal notation, we could. But I'm just going to go ahead and reduce this fraction. 60 and 8 are both multiples of 4, so 4 divides both of those. 4 times 15 is 60. So if we actually do the factoring and canceling, which you could probably reduce this in your head, but I'm going to go ahead and do the factoring and canceling. It's going to be 4 times 15 over the 4 times 2. So there the 4's cancel out. So ultimately we're left with u squared equals 15 over 2. And now we're ready to go ahead and extract roots. Again, we are dealing with a fraction here, or a ratio. So we're going to have to be careful with the notation when it involves the square roots. Okay, so now using the square root property, we have something squared equals a number, so we're ready to extract roots. So therefore, u is equal to plus or minus the square root of the 15 over 2. Now the issue here is typically we wouldn't leave our answer like this. We have a little bit of work to do. We can use one of the properties of square roots, and at this point you should be familiar with some of those properties. But when you take the square root of a ratio like this, you can actually take the square root of the top and bottom separately. So this would be the plus or minus the square root of 15 over the square root of 2. And at this point we can see that there's a square root in the denominator, and typically in algebra we don't like to leave a final answer like that. What we're going to do is rationalize the denominator. So in order to do that, we're going to multiply by something. We're going to multiply by the square root of 2 over the square root of 2. And essentially what we're doing to rationalize the denominator, we're squaring the denominator. And when you square a square root, under the right circumstances, those are inverse functions of each other. So they're going to cancel each other out. So now we're ready to tidy this up and give our final answers. U is equal to plus or minus. We can actually multiply the 15 and the 2 because they're both underneath the square root symbol. So we're going to get radical 30 all over. That's the square root of 4, but remember when you get the square root of 4, that's the same thing as 2. So we're going to write the bottom as 2. So the root 2 produces a root 4, which is actually 2. So we now have a rational denominator. So we've rationalized the denominator. So those would be the way we would produce our 2 roots. I'm not going to go to the decimal approximation on this one, but I'm going to go ahead and write it out as a solution set. So u would be equal to the negative of the square root of 30 over 2, and then the positive version of that. And there's the 2 roots to our equation. So this is kind of a basic example where we end up having to move a lot of terms around in the equation, and we had to deal with that square root in the denominator. So we do that by doing what's called rationalizing the denominator. All right, let's try one last example. This example is going to give us roots that are of what we call binomial type, and we might be able to work with the square root a little bit. We'll see. So we have a set of parentheses inside of this equation. Typically, we do what we can to get rid of parentheses when we're solving equations. But because we're using the square root property, we need to not square the binomial a plus 2 in this example. If we do square the a plus 2, we will no longer be able to take the approach of extracting roots or using the square root property. So we're going to leave the square alone. In fact, we're going to isolate that part of the equation. So it's really not that much different than the first example that we did. But let's move that 16 out of the way. So the inverse of 16 is a negative 16. So we're going to add a negative 16 to both sides of the equation. See where that takes us. We're left with 3 times the quantity a plus 2 squared equals, when we subtract 16 from 48, that's going to give us 32. Okay, so go ahead and continue solving. We're going to divide out the 3. So this is going to be kind of a complicated set of roots. But we're going to go ahead and divide out the 3. In order to use the square root property, we have to have the squared part of the equation isolated. So we're going to divide that out. So we're just left with the quantity a plus 2 squared equals this fraction 32 thirds. So we're definitely going to have to deal with rationalizing the denominator and that kind of thing. So this example is turning out to be actually quite a bit more difficult than the last two that we did. But we are ready to extract roots. So therefore we get the a plus 2 is equal to plus or minus the square root of 32 thirds. Now, before we isolate the a completely by adding a negative 2 to both sides of the equation, we're going to go ahead and work with the radical a little bit here, the square root of 32 over 3. So I'm just going to do that on the side. So we're looking at the square root of 32 thirds. I'm going to take the square root of the top and the bottom separately. So we will rationalize, but also at the same time, I'm noticing that the 32 is divisible by a perfect square. 32 is 16 times 2. So therefore, we can actually factor out the square root of 16, and then we get the square root of 2, and then it's still over the square root of 3. And we'll be able to take the square root of that 16 and just get 4 out of that. So even though 32 is not a perfect square, it is divisible by a perfect square, and that helps us in the long run. Now I'm going to also rationalize the denominator by multiplying by root 3 over root 3. And then we'll get that final presentation of that square root. So when you take the square root of the 16, you're going to get 4. So we're going to have a 4, and then that's going to leave us with the square root of 6, because root 2 times root 3 is root 6. So fit that radical 6 in there. And then that's all over the square root of 9, which is just 3. So that's the square root of 32 over 3 in its conventional form, or as you might call it, simplified form. And as you do this process, it doesn't seem like that was simpler, but it's following the convention at least. So we'll rewrite our equation. A plus 2 is equal to plus or minus, and then we're going to write this as 4 radical 6 all over 3. And then we just need to move that 2 to the other side of the equation. We'll subtract out the 2 on both sides using the additive inverse. And that does it for us. These cancel out, which we get a is equal to a negative 2 plus or minus 4 root 6 over 3. Now, technically, even though these are the two roots to the equation, when they're looking like this in binomial form, we typically would use the properties of fractions to put them together in a single ratio. And then from there, we can do the approximations. I can see the video is going a little long, so what I'm going to do is just give us at least the standard form of this answer. When I say standard form, I mean how we would typically see it presented in textbooks. Now these answers are not wrong. If you crunch these in a calculator, you're going to get the right answers. We're just going to put it together. So in terms of a fraction, 2 is like 2 over 1. And then if I want to see it as thirds, we would multiply it by 3 over 3. And that produces the fraction 6 thirds. So I'm going to go ahead and just write this thing as a equals a negative 6 thirds plus or minus 4 root 6 all over 3. And now we have the same denominator, and we can put this together as in a single ratio. So it's a negative 6 plus or minus 4 root 6 all over the common denominator of 3. So we can present our two roots. I'm not going to write them as a list this time, but we're just going to write out the separate roots. So we have a negative 6 minus 4 root 6 all over 3, or a is going to be equal to a negative 6 plus 4 root 6 all over 3. So this represents the two roots to our equation. And at this point now, if we wanted to, we can go ahead and use the order of operations to calculate this in a calculator. You've seen some of that in some of the other videos, so I'm just going to leave it alone for now. But you would just take the square root of 6 first, because that's the exponent. Exponents before multiplication. So once we take the square root of 6, multiply by 4, and then you have a plus or minus key in your calculator. You can make it negative, and then get that answer. Usually that means hitting the enter or equals key. And then subtract 6 from that, hit it, hit your equals again, and then you can divide out the 3, and that would give you the decimal approximation. This one down here is actually easier to calculate because of the plus sign in between those two things. But anyway, so this is the basic approach to solving quadratic equations. It's where we can actually just use the square root property. So the square root property, it is the easier approach to solving quadratic equations when the equations are set up to do that. And remember, the giveaway for that is that the linear part is missing. In other words, in this case, the variable a in this example, when we got down to the bottom where we're ready to extract roots, we were able to get just a plus 2 quantity squared equals a constant. And that's set up perfectly to do what we wanted to do, and that is to use the square root property. So anyway, thanks for watching this video, and just keep in mind that this is a limited technique. It works for a lot of examples. In fact, in physics, this approach works for a lot of problem solving. You don't always have to break out the more powerful formula, which we would call the quadratic formula. And we'll do that in a separate video.